This is the fourth lecture in strength of materials, and this is the last lecture for chapter 1. This lecture deals with what is known as thermal effects on different materials. Now, it's a common knowledge that when materials are heated, they expand. So, material heated leads to expansion, which means that their dimension increases. You might know the famous example of putting a steel ring around wheels of carts, which was done by first expanding the ring by heating it up, then putting it around the wheel, and then when it cools down, it will shrink and it will very tightly fit around the wheel. Now, this chapter deals with the mechanics of thermal stress and how to quantify it. Now let's see, we take a very simple example of what is seen normally in nature. So let's take a simple bar again. It's of length L, area of cross section is A, its Young's modulus is E, and it is, let's say, at a temperature of T0. So when it is heated, T0 increase to T final, or there is a change of temperature of this much. It has been seen that this leads to expansion of the dimensions of the bar. So this is the increase in its length. Now obviously we know that when there is a change of length, it is associated with a strain. So there is a strain here. It is given by the change of length over its original length. Now again, it has been experimentally found out that this is proportional to the increase in temperature or the change in temperature. So if we replace this formula with a constant of proportionality, we can write it like this. So what that means is that the strain is equal to a constant multiplied by the change in temperature. Normally this constant is denoted by alpha, and the relation is given like this. What this constant is known as coefficient of thermal expansion, and it is also abbreviated as CTE. It's coefficient of thermal expansion. C for coefficient, T for thermal, E for expansion. Now it is normally a property of material, which means that CTE is normally a property of material like E and nu and G and K, etc., which we have seen in the last lecture. Similarly, alpha is also a material property. Now, now let's see what happens if there is a strain. So the strain causes a change of length. Now obviously we have seen from previous lectures that if there is a strain, then there is a stress, but that's not the case with thermal expansion, especially the one which is free thermal expansion, which is like this. That this is a bar which is just kept on, let's say, a table, and it is expanding freely. Now in this case, there is no stress in the bar. Even though there is a Young's modulus of the bar, there is a strain, but there is no stress in the bar. Now apparently it seems that it is illogical or contrary to the knowledge because we know that this sigma is equal to E into epsilon. But we should also understand where is this sigma equal to E epsilon is valid. This is valid in those cases wherein there is a stress generated in the material, and we know from the definition of stress that stress gets generated when there is a load applied, and object resists that load. So if there is a load applied and the object resists the load, then across any cross section normal to the load applied, there is internal resistance built. That internal resistance is the cause of stress. In this case, in case of thermal expansion, there is no load applied, there is no resistance to any load. If we cut any cross section, we will see no force because there is no applied force. So there cannot be any reaction, because if there is a reaction inside, then it's an unbalanced force and the object should actually be moving, but it is not the case. So if there is no stress, if sigma is not there, sigma is equal to 0, which means that there is no stress, then how come the strain is there? This answer is obtained from material science. There is no stress, but what happens is when a material is heated, its internal crystalline structure or the internal molecular structure changes. Now when the molecular structure changes, it causes a realignment of the, let's say, the crystals, or in case of polymeric materials, the chains of molecules and all that, which causes the increase in the length. So please remember, in case of thermal expansion, if the expansion is free, which is that there is no resistance to expansion, then there is a strain, but there is no stress in the material. Now let's see what happens if we do the inverse experiment. What is the inverse experiment? We take a bar which is fixed on both sides, which means that the length is not allowed to increase or decrease. Now what happens when we heat this bar? Obviously, had this been not there, had this been like this, it would have expanded to this length, something like this. But what we are doing is that we are forcing this support to not allow this expansion. So in this case, we can take this in two parts. The delta T causes increase in the dimension, plus the support causing the change, the decrease in that same dimension by the same amount. So if this is delta L, this is minus delta L. Now this is a free expansion. This is free expansion. So there is no stress in this case. But this one is a forced compression, which means over here we have a strain which is equal to minus delta L upon, let's take L. And because this is forced, which means that the support is forcing the thing to go inside. So there's a stress which is, and of course there's a P. P is the reaction force, or the force caused, or the force which is applied by the support, which is equal to, so this is the compression or the compressive force which is applied on the bar. Now you see, in this case finally there is no strain, because the original length, this is the original length L, it remains same. This is the final length L. So there is no change in length, hence there is no strain. but there is a stress. There is a stress in the bar. So now this is the other case, or the reverse case, wherein there is a stress but there is no associated strain. While in case of free expansion, there is a strain but there is no associated stress. Now, apparently these defy the common logic that okay, if there's a strain, then there should be a stress, or vice versa. But we have to always remember the fundamentals of stress. The stress comes only in the case when there is a resistance built internally in the structure. Only then there is a stress. If there is no resistance built, there is no applied load, there is no resistance built, then there is no stress, and even though there may be strain. And similarly, the other case for stress, if there is an applied force which causes internal reaction, then obviously there is a stress. There may not be any strain because the length doesn't change. So the strain being a geometrical entity, which is the change of length, if it is not there, then there is no strain. But stress, which is the reaction to an externally applied agency, can still be there. Now, let's solve a couple of problems to understand this phenomenon better. Okay, I'll just go to a new page. So I take a very simple example first. There is one cylinder. It's hollow, which means it is a thin cylinder. Let's say that its length is L1, or the height is L1. It's placed on ground. Inside this hollow cylinder is another hollow cylinder, which is like this. Let's say this length is L2. And let's assume that the material of the first cylinder has coefficient of thermal expansion alpha 1. The second cylinder has material which has coefficient of thermal expansion equal to alpha 2. Now, what we do is we apply a change of temperature. We apply a change of temperature delta T to this, and the same change of temperature delta T to this one, which means that we increase the temperature. Obviously, this temperature has to increase and this object's temperature has to decrease, because this has to decrease in dimension, this has to go down, this has to go up in case we want to make them of equal length. So our aim is to find out what is the change of temperature which has to be applied to the two cylinders such that the change of temperature is equal for both of them. Okay, so let's solve this problem. Now, obviously, it's a simple problem. Let's say that the final length of both of them is equal to L. So L1 decreases to L, this goes down, and L2 increases to L, right? So this means decrease and this means increase. So what will this mean? That there's a strain epsilon 1, which is equal to the change of length, which is L minus L1 divided by the original length, which is L1. While in this case, in case of L2, there's a strain which is the change of length is L minus L2 over L2. Obviously, this is a negative quantity because L is smaller than L1. This is a positive quantity. So this strain is negative or compressive. This is tensile. This is epsilon 2. Now this can be written as alpha 1 delta t, and this can be written as alpha 2 delta t. Now here we have to always keep in mind that this delta t is negative because we have to cool the outer cylinder, while this delta t is positive because we have to heat up the inner cylinder. Now this delta t and this delta t, they have the same numerical value, which means that they will be either 5 or 6 or 10 or whatever, but this will be minus 5 and this will be plus 5. So what that means is we have to invert the direction of this equation such that both of them become positive. So I just take the absolute value of epsilon 1, which is equal to L1 minus L upon L1, and absolute value of epsilon 2 is L minus L2 upon L2. This is L, and this is equal to alpha 1 delta t, and this is equal to alpha 2 delta t. Now from these two equations, if we remove L somehow, how can we remove L? We can say L1 minus L is equal to alpha 1 delta t into L1, and L minus L2 is equal to alpha 2 delta t L2. Now we just add up these two equations, just add them. We have L1 minus L2 is equal to alpha 1 plus alpha 1 into L1, sorry, plus alpha 2 L2 into delta t. So if this is the equation, then obviously delta t is equal to L1 minus L2 divided by alpha 1 L1 plus alpha 2 L2. Now please see this equation or this result very carefully. What does that mean? Now you apply this to physical condition. Suppose both of them are equal in length, then obviously delta t is equal to 0 because we don't need a change of temperature to cause any change of length, because there is no change of length required. But it also gives a very good insight into what happens. Suppose you apply this formula without thinking. Now suppose I say that L2 is equal to 0, which means that the inner cylinder is not there. Now what happens if that is not there? Then obviously this L2 will become 0. So this is 0, this is 0. So what will that mean is that if we have a temperature delta T of 1 upon alpha 1, that will cause the first cylinder to shrink completely to length 0, because L1 has to become equal to L2. For that, this is the temperature required, delta T, which is given here. But that's non-physical, because if there is no cylinder inside, you cannot shrink an existing cylinder to 0 length just by a temperature change. That is like not following the conservation of mass, because suddenly the mass of the cylinder cannot vanish. So obviously these equations have to be applied with a lot of caution and conscientiousness, which is that we simply cannot apply them without understanding what they mean internally. So this is one important problem, and it is a very heavily used condition in many cases like pressure vessels, or in cases when we have to wrap up a material over a different material. In such conditions, this is the kind of equation which you will encounter. Now let's solve one more problem, which is like this. We have a simple bar. Its length is L. Its Young's modulus is E. area of cross section is A, and coefficient of thermal expansion is alpha. We heat it, delta T. So L becomes L plus alpha delta T into L. This is nothing but saying that the strain is equal to alpha delta T. Now strain is change of length over original length, which means delta L is equal to L into alpha delta T. Now change of length is the length final minus L, that is equal to L plus L into alpha delta T. So the final length is L plus L alpha delta T, or L 1 plus alpha delta T. This is easy, no problem. We can easily solve this problem and we can get the value of final length, or if we are given the final length, then what is the temperature required to cause that final length. Let's make the problem a lot more complicated. This is a very complicated problem which I am going to draw now. Same bar, spring attached to a fixed wall. Spring has a constant of K. The rest of the values are from here, same things. Now in this case, what happens is, if we heat the bar, it will expand, but when it expands, it will cause a compression of the spring. So the spring will put a reaction on the bar. So the delta T causes expansion this way, but the spring causes compression this way. So after some time, it will come an equilibrium with the spring. So let's say we have to figure out what is the change of length which is caused under this condition when there is a spring with a spring constant K attached to the free end of the bar. So this is the original length and this is the change of length, right? So now what happens? We have to isolate the bar. We take the bar alone. Had it been free, it would have gone to a length, a changed length of delta L, which is equal to L 1 plus alpha delta T. But now what is happening is that it cannot go to this full delta L. This bar is compressed by spring force. Now let's say that the final change of length is delta L and or some delta L dash. So this is the final change of length. So this was originally here and it finally becomes delta L dash. So if this is delta L dash, which means that we can say it first expanded to the whole length, which it would have done under free expansion, and then it got compressed by the spring force. Now at the equilibrium condition, the spring force is equal to the spring constant multiplied by the change of length of the spring, which is nothing but delta L dash. This is the spring force. Now this spring force causes a stress in the bar, and the stress causes the strain, and the strain causes a change in length from this direction. So the free expansion is this much, L 1 plus alpha delta T minus the change of length caused by the spring, which is K delta L dash is the force divided by AE This is the strain multiplied by the length. This is equal to the change of length, which is finally there. So please see this equation very carefully. This is the expansion caused by free thermal expansion minus what is happening because of the spring, which is this, is equal to the final length increase. Now we know what is the value of delta L dash from this. We can very easily figure out what is the value of delta L dash. So delta L dash, if you just rearrange this equation, you will find out that the value of delta L dash is equal to alpha delta TL divided by 1 plus KL upon AE. Now see, this is a very important result, in the sense that we can have a lot of insight into the physics of the problem here. Now please see, if we are given a problem in which there is no spring, obviously we can simply put K equal to 0 and we get free expansion. Now if in the other case there is a very stiff spring, if the K value of K is very high, then obviously the denominator increases and delta L value decreases, delta L dash value increases or decreases rather from the free expansion value to a very small number. If K is infinity, which means that the rigid wall is directly there, then obviously delta L dash is equal to 0. Now this equation can also be used in inverse condition, which is if I just write the equation again, delta L dash is equal to alpha delta T L divided by 1 plus KL upon AE. Now you see, in this equation we can also have a condition wherein if the area of cross section of the bar is very high or the E value is very high, if these are very high, then again the denominator, the change in the denominator, which is KL upon AE, will be very small. So 1 plus KL upon AE, that change from 1 to 1 plus KL upon AE will be very small number, which means that if the bar is extremely stiff or the bar has very high Young's modulus, then the spring force will not be able to stop that free expansion too much. On the other hand, if the value of Young's modulus is very small, in that case the spring will be able to stop it very easily. So if a very highly stiff bar, let's say of steel, is expanded and the value of K is not much, then the spring will not be effective against stopping the bar. This is a very practically important result. This is highly used in dimensional stability of materials under thermal expansion, wherein the expansion is stopped using some artificial means like putting a string or something. So the spring constant has to be such that it matches the required change in length. So if we have to restrict the change of length to a small number, then the spring constant has to be a very high number. You can see spring constant is inversely proportional to delta L dash here. So if you want to stop expansion, then a very stiff spring has to be used. And this is very important result in dimensional stability problems like those of machineries which are running at very high speed. For example, the wings of aircrafts, not the wings, sorry, the blades of aircraft engines. These blades are under extremely high thermal expansion and they are also rotating, so they are under extremely high centrifugal expansion. So both these expansions cause a very high change in the length of the blades. So there, if we have to restrict them to a small number, then we have to do some kind of artificial arrangement like this, or we have to take a material which is such that its alpha is small, because we cannot change delta T and L. They are governed by the combustion condition and the design. So if we cannot use a spring, then alpha has to be a very small number. And it is possible to make alpha very small by using composite materials, which are a different class of materials, wherein we can change the orientation of the material fibers and make alpha a small number. So this ends the first chapter, which is about the basic concepts of stress and strain. From the next lecture, we will see how to analyze the stresses and the deflections of beams. Now, beams are very important class of structural elements, and they are heavily used in almost all design activities. So we will see how to analyze beams in the next chapter.